In this video, we're going to talk about two things: the sampling distribution of sample means and the central limit theorem. Even though we've already had videos on the sampling distribution of sample means, I want to go over it one more time. This can be kind of a tricky idea, so I want to make sure that everybody really understands it and gets extra exposure. Then we're going to move on to talk about the central limit theorem, and we're going to go over some specific examples of the central limit theorem, how it's generally applied. Okay, let's get started. When we talk about the sampling distribution of sample means, we're underlying a process that sort of describes some of the random nature behind our general inferential statistics approach. So let's remember our approach. Suppose we have a huge population. Suppose we're thinking of what's the average height of an adult in the entire United States. All right, so our population here are adults in the United States, and that's entirely too big to study on its own. So what we typically do is we just take a representative sample, a random sample of that population, and we compute the sample mean. And the idea is that that sample mean, right, the average of the heights of the people we collected inside of our sample, should more or less be equal to our population mean, which would be the number we would get if we collected everybody's heights. Notice that this inferential statistics approach hides behind it a random process in that when we take a sample from that population, there's a lot of variation in the type of samples that could appear. So let's suppose we know how big of a sample we're willing to work with. We'll fix a sample size n, right? And if you want to think of n as being something like maybe 1,000. So we want to go out and collect a sample of 1,000 people. The truth of the matter is, if we're doing this at random, there's a lot of different samples that could appear by going out and collecting a random 1,000 set of people, right? So if I'm working across the entire United States, maybe sample 1 has 50 people from Massachusetts, whereas sample 2 has 150 people from Massachusetts, right? So each one of these samples, depending on the randomness of the sampling process, is going to be different. It'll contain different groups of people. And for that reason, each one of these samples is going to have a different sample mean. Okay, so what we can think of is if we're randomly selecting a smaller group of size n, or in this case, let's say 1,000, from our population, we're going to have a whole mess of different possible samples that could pop out by doing this random sampling process. And to really understand what we'll call the sampling distribution, what we want to do is look at what are the sample means that come out of each possible sample that we could take from our population. So the idea is as follows. In inferential statistics, we take a random sample, which means from the population, we're going to walk along a random one of these lines to the sample that we would, in practice, actually collect. And that'll lead to a sample mean. So what we want to do is think about all of these different possible sample means as being randomly determined by the sampling process itself, right? So depending on which group we get, we'll get a sample mean associated to it. And since these are randomly determined, we want to treat them as a random variable. So if we fix our size, our sample size n, then each sample is randomly determined. And as we mentioned, this means that the sample mean can be treated as a random variable, right? So we're going to give this sample mean a new symbol. We're going to call it capital X with a bar over it. And hopefully this is suggestive of sample means because little x with a bar over it were actual observed sample means, right? So since these sample means, which are randomly determined by our sampling process, can be modeled by a random variable, we can ask some very basic questions about this new sample mean. Right? First of all, what does this distribution look like, right? Is it going to be continuous or discrete? Is it going to have a bell shape like our normal distribution, or will it be something different? What's the expected value of x, right? What's the value of these sample means that will have sort of the most probability associated to it, the largest value for our density curve? We're going to represent this with a mu. This is our usual expected value formula, but we're going to put a little sub x bar to indicate that it's the expected value or the mean that we would expect for this random variable. And then finally, how much variation away from that mean do we expect to see? In other words, what's the standard deviation of this new random variable x bar? And we're going to denote that with our standard deviation symbol, but again, with a little sub x bar to indicate that it's the standard deviation for our actual sample mean random variable. So what's most important. Because we randomly sample from a population, the types of sample means that we would get are also randomly determined. So we treat this sample mean as a random variable, just like our normal random variable, just like our binomial random variables, right? So this sample mean, capital X bar, is a random variable. And we want to answer these questions. And the nice part about asking these questions is we actually have a very nice answer. There's a theorem called the central limit theorem that actually provides the answers to all three of these at once. So here's the general idea. Under certain conditions, which we'll talk about a little bit later, if you draw a sample of a fixed size n, right? So remember for our play example, we were thinking n is 1,000 if we're drawing from the population of the entire United States. Right? So if we draw a sample of n and we know that we're taking it from a population, assume that we have some mean mu and some standard deviation sigma, and this corresponds to your population parameters, then the random variable x bar is going to have a normal distribution. That's what our little squirrely n here indicates. The expected value for our sample mean random variable is the same as the mean for our population. Okay? So in terms of parameters, the means here aren't going to update when we start talking about sample means versus population means. What does update is your standard deviation. When we're talking about the standard deviation for x bar, the standard deviation of the sample means that we would see appearing, what we can do is take the standard deviation of our population, our original sigma, and divide it by the square root of n, or the square root of our sample size. This is going to give us a distribution for our sample means. So let's consider a quick example here. Suppose that the time spent on Facebook by employees at our company is normally distributed with a mean of 50 minutes and a standard deviation of 15 minutes. So in this case, these two parameters, the mean of 50 and the standard deviation of 15, these are population parameters. These are parameters mu and sigma that we know about a randomly selected individual employee. Now, if we start to group 10 employees together, so we're now collecting a sample of 10 from a larger population, we want to describe the distribution of the sample mean. So in other words, we want to describe the distribution of our x bar random variable, right? One thing that we notice coming out of our central limit theorem is that both distributions are normal. In other words, they're both going to have that bell-shaped curve, and both of them are going to use norm.dis and norm.inverse to make our probability or percentile calculations concrete. In terms of their means, for the population, the mean is 50, and what the central limit theorem tells us is that the sample mean random variable is going to share the same expected value. It's going to share the same mean, so this will also be 50. Now lastly, in the population, right, if your standard deviation is equal to 15, when we talk about the standard deviation in your sample means, we need to adjust this. So we're going to take our old standard deviation of 15 and divide by the square root of our sample size. In our case, we're randomly selecting 10 employees. So in this case, our sample size is 10. So we would take 15 over the square root of 10, and we would know that the standard deviation of this new sample mean random variable is 4.74. Okay? So now what we have is a nice probability distribution for the sample mean random variable. It has a mean of 50, a standard deviation of 4.74, and it's normally distributed. Now this gives me access to ask questions like, what's the probability that the mean time spent on Facebook among these 10 employees is, let's say, less than 45 minutes? We can answer that question using a normal distribution or using a norm.dist command inside of Excel. But when we identify what our parameters are, we're going to use 50 and we're going to use 4.74 rather than the original population parameters. So let's return to our simulation inside of Excel. So keep in mind, here's our setup. We have a population of scores here, and what I'm going to do is fix a sample size of 10. So what I'm going to do is randomly select 10 numbers inside of this population, and I'm going to compute the sample mean associated to those 10 randomly selected numbers. And I'm going to repeat this over and over and over again. Now, what we'll see on our graph is as we do more and more samples, we're going to start to see the shape of our actual sample means that we're collecting. In other words, this is going to give us a sense of the shape of our sampling distribution, the shape of x bar as a random variable. And we know that x bar as a random variable should be normal. So eventually, once we take enough samples to have a good data set, we're going to see a nice bell-shaped curve occurring in our histogram. Right? Down here at the bottom, we have the actual population mean and standard deviation. So these are the mean and standard deviation computed on all of the numbers in our population. What we have next to that are the predicted mean and standard deviations based on the central limit theorem. So in other words, we'll keep the mean the same, we'll adjust the standard deviation by the square root of our sample size. In this case, our sample size is 10, so you'll notice inside of our formula here, we've divided our population standard deviation by the square root of 10. Now the last thing we're going to do to show that the central limit theorem actually holds up in practice is we're going to look at, as we collect different sample means, we're going to keep track of them inside of this column M. We're going to look at what's the mean of the data set that we're going to create by taking all these random sample means, and what's the standard deviation. And what we should see is that once we have a large enough data set, these values are going to be pretty close to the predictions made by our central limit theorem. So let's see what happens. By clicking the Select Sample from Population, I randomly select 10 values. The mean of these values is 47.1. And you'll notice that I have now 1 bar in the 46 to 49 range in my histogram. So if I do this a couple of times, you can see that I'm little by little creating a data set of sample means. And the more points we collect in this data set of sample means, the more reflective it'll be of our x bar as a random variable. So the idea is to do this many times. So we're trying to take advantage of the law of large numbers. So what I'm going to do is actually run 100 samples at once, and then another 100, and then another 100, etc. until I've done this many times, right? So we're looking at, now I currently have about 1,200 samples taken from this population. And immediately what you notice is that the sample means as a distribution have this nice bell-shaped curve. So this is highlighting the fact that x bar as a random variable is normal. Now what we notice below with our approximations, our population and our population mean and standard deviation, these things are fixed, right? They were computed because we actually knew all of the values in our population. So we knew those for sure. Here are our predictions from our central limit theorem. The mean should be the same, but our standard deviation, right? Our standard deviation should update. Specifically, we're going to take our old standard deviation, the 12.75, and divide by the square root of our sample size, which in this case ends up giving us a 4.03. Now, if we look at the mean of column M, so this is an approximation of what the expected value for your x bar should be, you'll notice how close they are, 53.88 as opposed to 53.92. So the central limit theorem and what we see in practice are overlapping very nicely. The other thing you'll notice is that the same is true for our standard deviations. The standard deviations of this column M, all of these scores in our column, is about 4.16, which is very close to a 4.03. Okay? Now the fact that they're a little bit different, this is because we haven't actually considered every possible sample. All right, going back to our picture from before, we've only considered 1,200 of the very large number of possible samples that could occur, which would represent our sampling distribution. Right? But it gets us close enough to realize that even if we only look at the first 1,200 different samples, we can start to see the central limit theorem reflecting what we will see in practice. Now, if we were to actually add up every possible different way of sampling these numbers, we would get exact values here. But unfortunately, we don't have the time or the computing power to do that. So in our case, we're just going to be happy with this approximation. Okay? So again, the summary is, we have a general population, but the way in which we sample, right? Each time I do a different sampling method, I'm getting a different collection of measurements. So this is leading to different sampling means depending on the group that I select, right? That random group selection leads to random values for the sample mean. So we model that using a random variable. We call that random variable x bar. And we notice from this little visualization that x bar has a normal distribution, right? Nice bell-shaped curve. And the mean of these x bars is going to be the same as the mean in our population, but the standard deviation is going to be much smaller. Okay, so our standard deviation of the population in this case was 12. Now our standard deviation for a group of 10, right? The standard deviation for a group means of size 10 is smaller. It's going to be about 4 units. We mentioned that there are some conditions that we need to satisfy in order for the central limit theorem to apply. The first condition that we require is that the process by which we select our samples is a simple random sampling process. We talked about this at the beginning of the year, and moving forward we're going to assume that the way that we select the samples that we're going to work with always follow through a simple random sampling process. But the main idea here is that things like a convenience sample or a volunteer response sample don't fall into the category of a simple random sample. So you shouldn't be thinking that the central limit theorem should apply when we use these bad sampling techniques. The second, more important central limit theorem requirement is that one of two things follows, right? Either the population that you sampled from is normally distributed, or if you happen to have a population that is not normally distributed, or maybe you're not even sure what the distribution is, you just have to make your sample size large enough. So in particular, if you're unaware of what the distribution is for the population itself, and you can't guarantee that it's normally distributed, just make sure that when you collect your samples, you pick a sample size greater than 30. All right? It's this one that I want to give you a little bit further visualization and understanding for. So here's a population that I randomly created, and you can see it certainly doesn't have a normal distribution, right? It doesn't have one nice bell-shaped curve, and instead it seems to be trimodal. It has these 3 kind of random peaks inside of its population. So what I'm going to do is I'm going to randomly select different groups of certain sizes and take a look at what the sampling distribution more or less looks like. Here's what we get. If we take samples of size 2, right, so only 2 people in a group, this is what the sampling distribution looks like, right? This is what the histogram, like in our previous visualization, ends up looking like when we generate lots of different sample means where our group size is 2. And you'll notice the shape of this is not normal. The same is true for samples of size 3. We still don't have a normal looking shape for that sampling distribution. When you hit n equals 5, it gets a little bit better, but it's really at n equals 30 when we start considering groups of size 30 or more, even though our parent distribution is not normal, right? This is a highly irregular population, right? If you consider groups of size 30, the sample means still behave in this nice kind of bell-shaped curve shape, right? Once you go above 50 to 200, right, we're getting normal distributions consistently at this point. So our requirement here is that if you're unsure of what the population distribution is, or if you know it's not normally distributed, make sure that you choose a sample size that's 30 or more. And it's essentially to guarantee that your sampling distribution, your x bar random variable, has a nice normal distribution.